Okay, hello everyone. Originally, I wanted to move on to hypothesis testing, but probably the progress of our speed is a little bit faster than that I thought. So probably I will cover some last optional chapter of properties of point estimation, and also I will solve some additional exercise problems and finish the lecture for this week. Okay. Chapter 9.8 talks about some large sample properties of MLE. Actually, there are maybe two important large sample properties of MLE. The first one is consistency. So MLE is the consistent statistic, and the other is approximate normality. And this chapter 9.8 talks about approximate normality of MLE. Suppose t theta is differentiable function, then if we are interested in about t theta, then t theta hat is MLE of t theta. That's what we learned from the previous chapter. And for large sample size, this one, if we define this statistic, then this one follows standard normal with mean 0 and variance 1. This one would follow standard normal distribution, and in here Fy bar theta is the density function evaluated at random variable y. And I will not give you the full proof for this. Actually, this is very long story. So for here, I will just give you some intuitions why this one makes sense, and probably you can learn the details from the graduate school if you are interested. Maybe if you are very interested, probably I can give you the material to study, so you can ask me. So here we will define information statistic. So this is Fisher's information. I theta, we can define I theta this way. And um, and actually there's some more rules like Kramer lower bound. So there are some other theory related to this Fisher information, but I will skip it this time. And the approximate asymptotic normality of MLE is actually this one. There's a theorem that if the theta hat is MLE and theta is the parameter of interest, then square root n times this thing will follow normal distribution with mean 0 and variance 1 over information statistic. And this is the first one to prove. And by using delta method, you can prove that square root n times t theta hat minus t theta will follow this thing. And actually, from this distribution, this one can be directly proved. So from here, if you define your z like this, then this will follow normal 0, 1. And probably you may wonder what is delta method. Actually, delta method itself is very simple, but probably actually the delta method is that let this one as sigma square, let this one is sigma square. So the general version of delta method is like this. If any distribution follows like this, any statistic follow something like this, then by using delta method, if you are interested in t of theta hat, then the distribution would follow like this. So the delta method is something like this. If there's a if this is true, then this is true. Yeah, this is the delta method, and this prime is differentiation with respect to theta. So this is the delta method, and the proof for this is not very difficult, but probably you can learn this from also graduate school. So I will skip it at this stage. Okay, let's move on to example 9.18. For a random variable with a Bernoulli distribution, uh, with this, for y equals 0 or 1, if y1 to yn denote random sample of size n from this distribution, derive 100 times 1 minus alpha % confidence interval for p times 1 minus p, the variance associated with this distribution. Okay, so the problem is to derive the confidence interval for p times 1 minus p. And so we can think of that Tp is p times 1 minus p, and MLE is for Bernoulli distribution, MLE p hat is y bar. We know that. So and also from the previous theorem, we can derive the confidence interval can be derived this way. So so the problem for this is just calculating all the components. So for we know that Tp is p times 1 minus p, so the first derivative of that, the Tp dp, this one is 1 minus 2p, and we need this one squared, so this is the first component. And we will calculate this one, expected value of minus second derivative of ln p y given p. Okay, and so here ln p y bar p is that, so ln p y given p is y ln p plus 1 minus y ln 1 minus p. So we will get the first derivative. So to calculate this, let's differentiate it once. The ln p y given p, the first derivative is y over p, minus 1 minus p, here 1 minus y. Okay, and we will get the second derivative. P y given p is minus p square y, and here again minus 1 minus p square and 1 minus y. And we were going to get this one, and here actually what we know is that expected value of y is p. So so this one becomes here we have minus, so 1 over p minus plus this one is also 1 minus p, so 1 minus p cancelled. So so this one becomes this thing, and actually this one is p times 1 minus p, 1 minus p plus p is 1, and so we have this one. Okay, so now we are ready to plug them in. So p hat 1 minus p hat plus minus z alpha over 2 times square root of 1 minus 2p square, and this one p times 1 minus p go upside, p times 1 minus p, and divide by n is here, and we put p equals p hat, so p equals p hat. Okay, so this is the confidence interval that we get. From here, if you have data y1 to yn, your p hat is y bar, so plug this in here, then you will get the interval. Okay. Now let's move on to supplementary exercise problem 9.103. A random sample of size n is taken from a population with a Rayleigh distribution, as in exercise 9.34. The Rayleigh distribution is defined like this, and the first problem is find the MLE of theta. So to find the MLE of the theta, we need to firstly define our L theta. This is sum of multiplying I equals 1 to n, all the data probabilities, which is theta 2yi e to the minus yi square over theta. And for this one, this is 1 over theta nth, and 2 to nth, and I equals 1 to n yi, and also e to the minus sum of yi square divided by theta. And if we take log, take ln theta, then this will become n ln 2 over theta plus sum of I equals 1 to n ln yi and minus sum of yi square, yeah, this one. Okay, so to get the MLE, let's get the first derivative of this. So d theta d ln l theta, this is maybe it's easier to represent it as represent this as ln2 minus ln theta, and differentiate this thing. So this is now minus n divided by theta, and we are differentiating this one. So this is plus zeta square sum of yi square, and this one equals to 0. And so this one cancels, and so zeta hat equals sum of yi square divided by n. So this is our MLE. And actually we need second derivative here to make sure that this is maximum L zeta. Actually square is this side. For this one, plus zeta square n in here is minus 2 zeta third sum of yi squared. Okay, and here you put zeta equals zeta hat, which is n over sum of yi squared, or maybe you can replace this as n zeta hat. So that's n zeta hat second minus zeta hat third, and this is n zeta hat and 2, and so this one cancels, and so this is minus zeta hat square n, and this is less than 0. Because this zeta hat square is larger than 0, n is larger than 0, so minus positive is negative. So we can confirm that this is negative. So we can conclude that this is our MLE. And let's move on to the second part. Find the approximate variance of MLE obtained in part A. And to calculate this thing, and actually we need this. So for the MLE, it have approximate normality condition like this, and information is can be calculated as this. And so we want to find variance of zeta hat, and from here, from this equation, what we know is variance of square root of n zeta hat is 1 over information I zeta, and so this is n times variance of zeta hat is 1 over I zeta, and so we have variance of zeta hat. This is 1 over n times information zeta. So we know this one, and so now the problem B becomes just finding I zeta and put it in the equation. I will explain it in the next slide. Okay, so problem is to find the approximate variance of MLE, and we derived that the approximate variance is this thing. So what we need to calculate is just this information statistic and information feature information of zeta, and that's so firstly we need to get the second derivative of ln f y. So let's check what is ln f y given zeta, and this thing is from the formula here. If we take ln ln 2y minus ln zeta minus y square divided by zeta. Okay, so this is ln fy, and now we get the first derivative with respect to zeta, ln fy given zeta, and this is minus 1 over zeta here plus zeta square y square, and we get one more derivative. So one more derivative is plus 1 over zeta square and minus 2 zeta third y square. Okay, and so we would like to get that this thing expected minus expected value of this thing. So expected value of minus this thing is um, 1 over zeta square minus 1 over square plus 2 zeta square expected value of y square. Okay, and actually expected value of y square, let's put z equals y square here. Then what we know is that f z dz equals f y dy and dz dy. So dz dy. So fz is fy dy dz, and so this is dy dz, dy dz, dy y equals z 1 over 2, and so dy dz is if we dy dz is 1 over 2 z to the minus 1 over 2. So in fy y is z 1 over 2, so this is so fz is f z y z y here z 1 over 2, and this thing is 1 over 2 z to the minus 1 over 2, and so fz dg fz z becomes 2z 1 over 2 over theta e to the minus z over theta and 1 over 2 z minus 1 over 2, and this one cancels and 2 cancels, and now this thing becomes 1 over theta e to the minus z over theta. So if we put z equals y squared, then we can find that z follows exponential distribution with theta. So expected value of z is theta, and here actually z is y squared. So this expected value of y squared is theta. So in this expression, this one becomes this is third. This one becomes minus 1 over theta square plus 2 over theta square, which is 1 over theta square. Okay, so yeah, so now we calculated our information theta. This is I theta, and this I theta is 1 over theta square, 1 over theta square. So the variance of theta hat is theta square over n. Okay, so this is our variance. Okay. Okay, let's move on to supplementary exercise 9.104. Suppose that y1 to y1, y2, yn constitute a random sample from the density function of this, and actually, as you may guess, this one is shifted exponential distribution. So from here you can check that y minus theta follows exponential distribution with parameter 1. Okay, and where theta is unknown, the shifting parameter is unknown parameter, positive constant parameter. And let's try to solve these. Number A, find an estimator theta 1 hat for theta by the method of moment. Okay, let's firstly solve this number A. To solve the method of moment, what we need to know is we need to calculate expected value of y, and actually expected value of y, we know that from here expected value of y minus theta is 1. So expected value of y should be theta plus 1. So and for by using method of moment, we will put it as the first moment, sample mean y bar. So our estimate, theta hat estimate with method of moment should be y bar minus 1. Okay, so this is our estimate with method of moment. And let's move on to number B. Find an estimator of theta 2 hat for theta by the method of maximum likelihood. So for this, we firstly need to find likelihood function of theta. And this is actually multiplying all density functions, so which is e to minus sum of yi minus theta. And actually this one is e to the minus sum of yi plus n theta. And what we can see is that this is the likelihood function, and there's also constrictions. Y's are greater than zeta. So here is zeta, and um, if we order these y's, then probably y1 to y dot dot dot, and um, and we can find this relationship, and what we can see is that this function is increasing function with respect to zeta. So um, so this one is actually e to the minus sum of yi times uh, e to the n zeta, and this e to the n zeta is this one is constant, this one is increasing function with respect to zeta, and so the larger the zeta, the likelihood is greater. So the one that maximizes this likelihood is y1. So zeta hat MLE is the minimum of yi's, because this L zeta is increasing function with respect to zeta, and so the larger the zeta, the greater the likelihood is, and how the maximum value that we can get for zeta is y1. So this is our maximum likelihood. Okay, and let's move on to number C, and I will explain number C from the next slide. Okay, let's move on to number C. Adjust zeta 1 hat and zeta 2 hat so that they are unbiased. Okay, let's try to do this first. So zeta 1 hat is method of moment estimator, which is y bar minus 1, and actually expected value of y, y minus zeta was 1, because y minus zeta follows exponential distribution with parameter 1, and so expected value of y is zeta plus 1, and so expected value of zeta 1 hat is again since expected value of y is zeta plus 1, this is zeta plus 1 minus 1, so this is zeta. So this one is unbiased estimator. And what about zeta 2 hat? And zeta 2 hat, zeta 2 hat is maximum likelihood estimator, which is the minimum of yi's. And to do that, we need to derive the density function of this order statistic. And to calculate the minimum, the density function of this, actually you can check the theorem, theorem 6.5. 6.5. By using theorem 6.5, you can derive the density function. This is n times 1 minus f of y to the n minus 1th and fy. And this is n times 1 minus fy. It's actually integrating the probability of y is greater than y. So this is integrating from y to infinity e to the minus y minus zeta and dy, and this is minus e to the minus y minus zeta from y to infinity, and putting infinity is 0, so this is e to the minus y minus zeta. And actually, yeah, so this is this part is e to the minus y minus zeta to the n minus 1th, and fy is e to the minus y minus zeta. Okay, so this is n times e to the minus n times y minus zeta. And what's this density function? And actually from here what we can see is that the y1 minus zeta, this thing follows exponential distribution with 1 over n. So this is shifted density function. This is again shifted density, shifted exponential distribution, and with theta 1 over n. And so what we can check is that expected value of y1 minus theta is 1 over n, and so expected value of the first order statistic is theta plus 1 over n. And so to make this one unbiased estimator, the unbiased estimator is y1 minus 1 over n. So this one is unbiased estimator. And find the efficiency of the adjusted theta 1 hat relative to adjusted theta 2 hat. So we want to find the relative efficiency. So EFF theta 1 hat comma theta 2 hat star, and this is variance of theta 1 hat, and here variance of theta 2 star. Okay, and actually we can use this distributional thing again. So variance of y1 minus theta is actually variance of y1. They are same, and this thing is 1 over n square. And also from here, from this one, variance of y minus theta is 1. So variance of y is 1. Okay, and so from here you can check that the upper part is 1 over n square, and the this part we want to calculate variance of y bar minus 1, and actually this is variance of y bar, and this is actually variance of y over n, and variance of y is 1, so this is 1 over n. So this is 1 over n, so this is 1 over n. Okay, so this is the relative efficiency. Okay. Okay, so this is end of the chapter 9. Today we covered the last optional chapter, and that was about asymptotic normality of MLE. And we also solved some supplementary exercise problems. Um, uh, and 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 so and in next week we will going for the hypothesis testing. And thank you and see you next week.